Okay, so we saw a bit of instructions, and those were those add and move, complement, decrement, moving between registers, etc. And we'll continue. Now, this data type, how many types of hexadecimal representations are there in PIC? So here there is a literal value being moved into working register, and this is specified as 99 followed by a capital H, which denotes hexadecimal, or it could be a small h, doesn't matter, case doesn't matter. Or you can precede the 99 with a 0x in small case or 0x in capital case. Okay. Or you can just write 99, nothing in the front or back. So which means the default it takes as hex. That's the meaning. We just type 99, it will accept it as 99H. Okay, as hexadecimal. And you could also write small h and then within quotes 99. So these are 4 representation of hex. Okay. Now here I have written these two are invalid because if this digit starts with a hex alphabet, it should be preceded by a 0. So it should be 0E5H. Here also add LWC6 because starting is an alphabet, you should proceed with a 0. That is why it is invalid. So just note that if this hex starts with an alphabet, you should have a 0 preceding it. I hope you are seeing it and I am audible. I'll just check if anything is there in the comment, in the chat box. I hope it's okay. Now I'll continue. Okay. This system is slow. So hope you are seeing the presentation as well as the audio was okay. So that's why I typed in the chat. Someone please respond. Okay then. So as a default, the PIC accepts hexadecimal, and if the literal value starts with the alphabet, you should precede it with a 0. And regarding binary, you should write B or a small b, as well as put in quotes, the single quotes, the 8 bits. So this is how you should represent binary number, which is a literal value put into the working register. So this is the representation for binary. So hexadecimal, binary, and then decimal. Suppose to the base 10 you want to put a value, you should write D or small d and within single quotes the value. This will be treated as a decimal. Or there are 2 ways. You can put a decimal and then write 1 2, it will be accepted as a decimal. So we had seen hex, 4 ways to represent hex, 1 way to represent binary, 2 ways to represent decimal, and an ASCII. Suppose you want the ASCII for 2 within a quotes, you precede it with a capital A, or you just write like this capital A or small a. So for decimal D, binary B, ASCII A, and hex H. So that will treat it as a ASCII value if it is A, or it will treat the literal value as decimal if there is a D, or it will treat as a binary or hex. So these are the 4 types of data you could input. And let's go to the a program. When we write assembly, normally the instructions tell CPU what is to be done. So you write add LW some value to working register, you are adding something, that is an instruction for the CPU. Now directives or pseudo instructions are directions to the assembler. So you give some directions to assembler, those are called directives. Okay. Now one such directive is EQU, equate. So this is an example in which you equate 25 hexadecimal to a variable count. So this EQU associates a constant number with a data or a address label. So this could be an address label. So or something, some address, it could be 25H, that could address. So you write like this. So this associates a constant number, this number, with a data or a address label. So wherever there is a count appearing in the instruction, that would be replaced by this 25 hex. So that's the meaning of this. So this is not an instruction to be executed by the CPU. This is an direction to the assembler. So those are called assembler directives. Now here move LW count means you are moving to a literal value to working register, which is count, and that count is equated as 25H. So 25H will be moved to this W. So port B you can equate as 07 hex. So SFR port B address is, so whenever in a program you are referring to port B, you would be referring to this address. So that is the meaning of this EQ. Similarly, there is a set instruction. The only difference is the value assigned by set may be reassigned later. Okay, so set is similar to EQ. Only thing is that you can reassign the value in the case of set. So I have pressed for the next slide. It's taking time. Okay. ORG means you write a piece of code somewhere in the memory. Okay, that address, so where it starts, that address is specified. So assembler should know, assembler is assembling it into an executable one, so it should know where the program starts. So you will write org, the beginning of the address, in hex. Okay, now where up to what point there is code, or up to what point there are instruction, and beyond that you need not look at it, that is specified by end, the end of the source file or assembler file. Anything after that can be ignored by the assembler. So assembler would focus on the lines of codes between org and end. Now list. Now there are a lot of chips. So this instruction would specify the specific chip within the PIC18 family you are referring to. So that should be included, like list P equal to 18F452 means the code is meant for PIC18 family and specifically for this chip. So this is a direction to the assembler. The assembler, the specific PIC chip for which the program should be assembled. Okay, that is the meaning of this instruction. And hash include means the libraries associated with this chip. This chip. So chip should be specified. The start and end of the program should be specified. The chip should be specified. And radix numbering system is hexadecimal or decimal. Default is hex. So we saw that default is hex. If we use radix DEC, interpret it as DEC, decimal. So by default, assembler would take any data as hex. So you want to change the numbering system. This is the directive to the assembler. You can treat everything as decimal. That is what is meant by this directive. So this is a sample assembly language program. We had seen that a format of an instruction could have a label which is optional, mnemonic, say move, add, the operation part. The operand part may not be there in some instructions, so it is in square bracket, it is optional. Say no operation is a mnemonic which doesn't have an operand, and comment also optional. So here this is a comment, pick assembly language program to add some data. Again a comment, store sum in file register location 10H. So here sum is equated to 10H. So RAM location 10H for sum. So whenever you are referring to sum, it would be RAM location 10H. So the sum is the addition of some data is written in sum, which is stored in sum, and the location is 10H that you have specified here. And this is a directive to the assembler. Next, org 0H. So you start the program from 0. So whatever is there in the memory, address 0 onwards, you treat it as a code. Then some piece of code is written here. You move to WRG some value. You add some value to what is already there in WRG. Again you add. These are all hex. Now this is decimal. Decimal, it is converted to hex here. Okay. Because already there is hex. So when you provide a decimal, it has to be converted to hex and it is added. And here again something to be added is given in hex. Again something to be added is given in binary. That would be converted to hex and then added. Then finally what is there in the working register is moved to sum, and this sum is defined as this memory location using this directive. So whenever you move something to sum, it is to this location you are saving. So the sum is saved in the location. Here go to here. You are saving here. Now end. End means origin and end. Origin is where this piece of code starts, and end is somewhere you end the code. So after that you can ignore anything. So this assembler gets this much of information using these directives, specifically here EQU, ORG and end. Now for labels, the label should be unique. So labels are used for go-to statements or jump statements, branching instruction. So you should give a label. and first character should be alphabet, and we should not use reserved words like move and add as labels. Okay, this we had seen it earlier. Now these are the normal steps to create a program. So we haven't come across this MP Lab integrated development environment. We can use that environment to visualize the contents of the registers, and we'll come to that. Anyway, you have a lab. Gobi sir will be handling that lab. So I will be just going through all these things, and you have to do all these things. So when you do all these things, you would write in an editor, and that extension would be some name .asm, and you give it to the assembler program. So this is the source. ASM is the source. You get the object. This is assembled. Mnemonics converted to hex, and which can be converted to binary. And here there would be additional library files, maybe include many library files corresponding to that specific PIC18 family chip. So that is linked, and then finally you create this object file is out. Okay, so this is the out object file. Again, this is a debug file, and there are many other files. So you will come across that later on, and whatever is linked, and this is downloaded to the ROM of the PIC, and it will be there in the ROM. And it could be a program you have written for a timer or any device like washing machine or anything. You can write a program, and you can use this MP Lab IDE to simulate that program. So these are the steps. So whenever there is some error in the compilation, it will show error. You should recompile it by correcting the errors. So here, these are the lines we have written in the previous program. So these are all just comments, and here in this line you are equating sum to the location, and here this is the org. Here these are all additions, and here you have the end, and these are all the comments. And now for every mnemonic and this operand, so you see this 25H is there, 0E is for this mnemonic. So here there is 34, and 0F is this add LW, 11H is there, and 0F is corresponding to this mnemonic. Mnemonics are for humans to understand. These are for machines to understand. Okay. Now, after having done all this, now I think it is duty of machine. So into a language which the machine should understand, and into some locations. Okay. So this is called the list file. Finally, the memory location starting from 0 and somewhere up to E, what are the patterns of ones and zeros, which is represented by hex here, will be, instead of this will be assembled into this one. So this one, this whole thing which is English like, is assembled into this one, left side. This is the list file. It shows both. So here, these are the ROM contents. From 00 up to this location, you have this. So list file shows the binary. So in the list file, both this source file in mnemonic and the binary is there. Okay, so finally you get this one. Starting from a location which is 000, wherein you have this 0E and 25. So whether you should put 0E in the first address, because each location is 1 byte. So these are 2 bytes, 2 byte instruction. We'll come to that. So only 1 byte can be put in one address. Then the next address you should put the next byte. So which one to put? Whether you should put this higher byte in the 0 address or this 25 in the 0 address is defined by the endianness. So there is a little endian and big endian convention. So that will come to later. So whether you put 0E or you put 25 first is depending upon whether that processor follows little endian convention or big endian convention. A certain processor follow little endian convention, certain processor follows big endian convention. It is just the matter of putting which one first in the lower address. And once you put like that, everything should be like that. You should be consistent. Now we come across to program counter. Program counter is you are fetching instructions. Okay, these are all instructions. So this instruction is in this location. Now next, this instruction should be fetched from this location. These are lines of assembly code, whereas the locations are here. Okay, so from this you have to location, you have to fetch this, and from this location next one. Likewise you are executing. So when we look at the assembly, only we will consider it as a full instruction. Here also next instruction, next instruction. These are all bytes. So actually instructions are there in the row. Now a program counter is a specific register which is of length 21 bit. So 2 raised to 21 is 32 MB. So 32 megabyte of code can be accessed using 21 bits. So actually this ROM can have 32 megabytes of size maximum, because there are 21 bits available in the program counter, or the size of the program counter is 21. The program counter is a register which keeps track of the address of the location from which the next instruction is to be fetched. So always it is fetch, decode, execute, fetch, decode, execute. So just does that. The processor just does fetch, decode, execute. Next one, fetch, decode, execute. And from where to fetch? Fetching is from a memory, and you have to specify an address, and that is specified by the program counter. Since it has 21 bits, it can address 2 raised to 21 locations, which is 32 MB. So find the ROM memory address of each of the following PIC chips. So here, if the memory is only 4 KB, which is 4096, okay, so the address location would only be this one, 0002 0FFF. You can map this. So if the memory is higher, you would have a larger address space, and if the memory is, this is KB, so you have this one, this address space. So different chips comes with different ROM memory. So if you have to write a program for a small device, you need only say 4 KB of memory, then this would be sufficient. Or if you need only 16 KB of memory, this would be sufficient. You need not buy a chip with a large memory size, because these microcontrollers are for devices. They are implemented in the devices. Okay, microcontrollers are doing a specific function again and again repeatedly. So they may not be They may not be requiring large memory, so you should choose the PIC with suitable memory for your application. So a PIC, this one has only this much of memory ROM, and this PIC has a larger memory, and this PIC has a still larger memory, and the maximum value is 32 MB because program counter has that value. So when whichever PIC you are referring to, you can download the data sheet. ഈ സിമുലേറ്റർ ചെയ്യുമ്പോഴും ഒരു പിക്ക് സെലക്ട് ചെയ്യണം നമ്മൾ. അപ്പോൾ ആ പിക്കിൻ്റെ ഫീച്ചേഴ്സാണ് നമ്മൾ അറിയേണ്ടത്. You would be selecting a particular chip. There would be a number for that chip. The ROM size would be different, and it is not a general thing. So you should know that it varies within the family of PIC18 itself. So the PIC microcontroller, regardless of family, wakes up at memory location 0 when it is powered up. Whatever be the PIC18 chip, it always has the first address as 00. ആദ്യത്തെ ROM, ആദ്യത്തെ instruction 000 like, regardless of the family. Okay. So even if it is PIC16 or PIC14 also, it should be 000, should be the starting address. So actually we are achieving this by using ORG statements in the source program. As we have seen earlier, we should write the start and end. Start is ORG. So this is the list file which we had seen earlier, and these are the contents. So there is only say 1, 2, F is 15, 16, 17, 18 memory bytes of memory is all that needed for this program. So you need not go for a PIC with a very large memory size. If say a remote of a TV has only a few memory, you can use that. Now, so program counter is 21 bit. Program counter is 21 bit. Now, the ROM has the code. Now, earlier what I had written was every location had only 8 bit. Earlier, in the previous slide, I had written like that, 8 bit. Actually, this is organized as 2 byte wide. So high byte and low byte is there. So 16 bit wide. So 0 is here, 1 is here, 2 is here, 3 is here, 4, 5, like that. So rather than 0, 1, 2, 0 which is the low byte, 1 which is the high byte, 2 which is again the low byte, high byte. So it is 16 bit width. So each location is considered to be 16 bit wide. Why we are doing is, see the data bus. Data bus is D0 to D15. Okay. Address A0 to A90 means only 20 bits you are getting. Actually, I told 21 bits. So 1 bit is from somewhere else. So I didn't complicate things much. For the time being, you consider that 21 bits are there, 21 wires are there, A0 to A20. So in this PIC, actually, I didn't put that here. So here I had just put 21. Now here, when you look, there are only 20 here, A0 to A90. However, data is 0 to 15. So here is the ROM where you write the code, and it is shown 16 bit. How it becomes 16 bit is, you are putting it side by side. So 16 bit, 16 bit, like that. Why you are making it 16 bit? Because you are able to bring in 16 bits at a time. ഒരു ക്ലോക്കിൽ 16 ബിറ്റ് നമുക്ക് കൊണ്ടുവരാൻ പറ്റും. നമ്മൾ 8 ബിറ്റ് കൊണ്ടുവരികയാണെങ്കിൽ 2 ക്ലോക്ക് വേണം. അപ്പോൾ നമ്മൾ സ്ലോ ആവും. അപ്പോൾ നമ്മൾ like a 8 lane traffic and like a 16 lane traffic. When you have a 16 lane traffic, you can transport 16 say bits in 1 clock. So that would be faster. So that is why rather than having this 1 byte structure, this ROM is having this 2 byte wide, so that you can bring in more bits at a time. Now I told you that this 25H is there and 0E is there. 0E is the opcode and 25H is the data. In the first line, you are bringing in 25H into the working register. So move LW 25H means 25H is the literal value and move LW 0EH. Now in the lower byte you put this one opcode, and in the higher byte you put this data. So this is this little endian concept. The lower byte go to the lower memory location, higher byte goes to the higher memory address. So when there are 2 bytes, where you should put, so this PIC18 follows this little endian system. Had it been big endian, it would have been 25H here and 0EA here. So all these would change. However, for PIC18 it is like this. അപ്പോൾ ഇതിൽ നമ്മൾ ഒരു പ്രോസസ്സർ ലിറ്റിൽ എൻഡിയൻ ആണ്, വേറൊരു പ്രോസസ്സർ ബിഗ് എൻഡിയൻ ആണെങ്കിൽ ഇവിടെ കുറച്ച് എന്തെങ്കിലും നിങ്ങൾക്ക് ഒരു ചേഞ്ച് വരുത്തേണ്ടി വരും. ഒരു porting from one processor to another, a list file, one which is having a little endian thing and one which is having a big endian thing. You should be careful. This would have been the data and this would be the opcode. Otherwise, in another processor, maybe in 8051, I don't know how it is, it could be different. So അപ്പോൾ അവിടെ നിങ്ങൾ ഇത് ശ്രദ്ധിക്കേണ്ടിയിരിക്കുന്നു. പിക്കിൻ്റെ എല്ലാത്തിനും same thing. So how you put the lower byte and how you put the higher byte, you should know that in PIC you follow this one, little endian concept. Now this I had shown earlier. Von Neumann architecture le Harvard architecture different ആണ്. നമ്മൾ ഇത് ഹാർവാർഡ് ആർക്കിടെക്ചർ ആണ് യൂസ് ചെയ്യുന്നത്. Okay. So whole thing you can just visualize this as a data as well as code is addressed by one set of address bits, and data as well as code is brought into the CPU by one set of data bus in von Neumann architecture. Since this whole memory is considered as a single unit and there is only one address bus and only one data bus in von Neumann architecture. Whereas in the PIC, which is Harvard architecture, you have a address bus for the memory as well as address bus for the data as well as data bus for the code as well as data bus for the data. But 4 ബസ് വേണം. അപ്പം 4 set of buses. ഓക്കെ. അപ്പോൾ നമ്മളൊരു കമ്പ്യൂട്ടറിലാണെങ്കിൽ നമ്മൾ ഈ ഹാർവാർഡ് ആർക്കിടെക്ചർ കൊണ്ടുവരുമ്പോൾ ഈ ബസ് ഇപ്പോൾ വിൻഡോസ് ഒക്കെ 64 ബിറ്റ് ഒക്കെ ആണെങ്കിൽ ഇവിടെ 64 ബിറ്റ്, ഇവിടെ 64, അപ്പോൾ അതിൻ്റെ അഡ്രസ് ബസ്. അപ്പോൾ അത് പക്ഷേ ഈ മൈക്രോ കൺട്രോളറിൽ മെമ്മറി സൈസൊക്കെ കുറവും ഈ മെമ്മറി എല്ലാം ഒരു ചിപ്പിനകത്താണ്, മൈക്രോ കൺട്രോളറിനകത്ത്. Everything is residing within the chip. So this Harvard architecture can be implemented within a chip. In a computer, everything is not within a chip. So this would be in different places outside and you have to run 4 set of buses. It is very difficult. It is easy to implement in a microcontroller, the Harvard architecture, than in a PC, it is desktop, it is difficult. So normally this is the case in our PIC18 family, because all memory is within the chip. You can afford to have 4 set of buses, 1 set of address for the code, 1 set of address for the data, 1 set of data bus for the code, and 1 set of data bus for the data. Now we'll just see few more slides and stop. Just to note that a move LW instruction, so almost all instructions are 2 byte. So in move LW, which is a literal value, 8 bits are for the literal value and 8 bits are for the opcode. 16 bit ആണ് ഇത്, 2 byte ആണ്. Add LW ലും literal value ന് 8 ബിറ്റും opcode ന് 8 ബിറ്റും, അതും 2 byte ആണ്. Move WF, working register in file register, ഇവിടെയും 8 ബിറ്റ് opcode ഉം 8 ബിറ്റ് literal value. ഇതില് ഈ 8 ബിറ്റ് ഓപ്കോഡിൽ 1 ബിറ്റ് ആക്സസ് ബാൻഡ് സ്പെസിഫൈ ചെയ്യാൻ ഉപയോഗിക്കുന്നുണ്ട്. അപ്പോൾ എഫക്റ്റീവ്ലി യു ഗെറ്റ് ഓൺലി 7 ബിറ്റ്സ്. അപ്പോൾ ഇൻസ്ട്രക്ഷൻ സൈസ് പറയാം, ഇൻസ്ട്രക്ഷൻ സൈസും നോർമലി 2 ബൈറ്റ്, പക്ഷെ ചിലത് 4 ബൈറ്റ് ഉണ്ട്. മൂവ് ഫ്രം 1 ഫയൽ രജിസ്റ്റർ ലൊക്കേഷൻ ടു അനദർ ഫയൽ രജിസ്റ്റർ ലൊക്കേഷൻ ഇസ് 4 ബൈറ്റ്. അപ്പോൾ 16 ബിറ്റ് ഓപ്കോഡ്, 8 8 16, and 16 bit opcode and address of source file register. So this is 16 bit opcode and address of source file, and 16 bit, this totally 16 bit. So this is an opcode and this is address of source file, this is an opcode and this is an address of destination file. So the source file and destination file are represented using 12 bits and 4 bits for this opcode and 4 bits. So this is somehow split as 4 bytes. So this is 8 8 8 8, and this 12 forms the source file location and this 12 forms the destination. So this is how, this is a 4 byte instruction. And go to is also 4 byte. So here you have 12 bits of opcode and these are the target address. You are going to some place. Okay. So here K0 to K19, and this program counter, 1 bit comes from some other place which I will mention later. Okay. So program counter 21 ആണ്. ഇവിടെ നമുക്ക് 0 മുതൽ 19 വരെ 20, പിന്നെ ഒരു 0 വരുന്നുണ്ട്. That I will tell later. So you just keep in mind. So you just keep in mind that instructions are mostly 2 byte, mostly whatever we come across, but certain instructions are 4 byte. In a RISC architecture ne patti ഞാൻ നേരത്തെ പറഞ്ഞിട്ടുള്ളതാണ്. 8051 CISC ആണ്. അതിൽ 1 byte instruction, 2 byte, 3 byte instruction ഒക്കെ ഉണ്ട്. ഡീകോഡിംഗ് ഡിഫിക്കൽട്ട് ആണ്. കണ്ടമാനം രജിസ്റ്റേഴ്സ് ഉണ്ട്. ഓക്കെ. അപ്പോൾ ഇവിടെ റിസ്ക് ആർക്കിടെക്ചറിൽ ഫിക്സഡ് ഇൻസ്ട്രക്ഷൻസ് മിക്കവാറും എല്ലാം 2 byte ആണ്. മിക്കവാറും എല്ലാം 2 byte ആണ്. പിന്നെ കണ്ടമാനം രജിസ്റ്റേഴ്സ് ഉണ്ട്. അപ്പോൾ സ്റ്റാക്കിൻ്റെ യൂസ് കുറയ്ക്കും. പിന്നെ നമ്പർ ഓഫ് ഇൻസ്ട്രക്ഷൻസ് 77 ഉള്ളൂ. അപ്പോൾ അസംബ്ലി ലാംഗ്വേജ് പ്രോഗ്രാമിംഗ് 77 ഇൻസ്ട്രക്ഷൻ ഉപയോഗിക്കുന്നുള്ളൂ. പിന്നെ മിക്കവാറും 95% instruction executed within 1 clock cycle. So these are all advantages of this RISC. So separate buses for data and code. It follows Harvard architecture. And ഒരു ഇൻസ്ട്രക്ഷൻ ഡീകോഡ് ചെയ്യുമ്പോൾ നമ്മൾ ഹാർഡ്വെയർ ആയിട്ടാണ് ഇൻസ്ട്രക്ഷൻ ഡീകോഡ് ചെയ്യുന്നത്. ഹാർഡ്വെയർ, അതിൽ മൈക്രോ കോഡ് യൂസ് ചെയ്യുന്നില്ല. ഇനി ലോഡ് സ്റ്റോർ ആർക്കിടെക്ചർ, അപ്പം നമ്മൾ ഒരിക്കലും ഒരു ലിറ്ററൽ വാല്യൂ എപ്പോഴും നമ്മൾ വർക്കിംഗ് രജിസ്റ്ററിൽ കൊണ്ടുവരും. അല്ലാതെ ഒരു റോം ലൊക്കേഷനിൽ നേരിട്ട് നമ്മളൊരു വാല്യൂ ആഡ് ചെയ്യില്ല. ഒരു വർക്കിംഗ് രജിസ്റ്ററിൽ നിന്ന് നമ്മൾ മിക്കവാറും എല്ലാം വർക്കിംഗ് രജിസ്റ്ററിൽ കൊണ്ടുവന്നിട്ടാണ് ആഡ് ചെയ്യുന്നത്. അതാണ് ലോഡ് സ്റ്റോർ. സോ വിൽ കം അക്രോസ് ഓൾ ദീസ് തിങ്സ് later on. So for the time being, you note that we have a lot of instructions, and all these instructions are mostly the instructions are 2 byte. Mostly the instructions are 2 byte, and